Right, so it is 10 and we will get started for today. So announcements, some general class announcements. Remember your test 2, is this upcoming Wednesday. We already went over one slide from this current PowerPoint, the one for Wednesday, March 10th. And just looking ahead, there's no way that I can cover this one and the one I put out for today. So what's going to happen is this Wednesday, March 10th PowerPoint is going to be the last one for test 2. And I already created a test 3 folder that has the PowerPoint for the one I developed for today. And since I'm not going to make it through all the way through the PowerPoint I had for today, the plan is the folder I currently have for Monday, I'm going to push that back and push all the other folders back. So I'm going to redate it, which means that this Monday there's no quiz or reading guide due. There is homework still. So make sure you still do the homework that was originally due for Monday. That's not being pushed back, just the folder. And I'm not pushing it back to Wednesday. So Wednesday on test days, I'll never have a reading guide quiz due. So the Monday folder is going to be pushed back to Friday, and then everything will be pushed back accordingly. If you already did the stuff for Monday, then you're set until Friday. If you didn't do it yet, then no worries, it'll be due on Friday. So before we get into things, are there any questions people might have? All right, no questions. So, looks like we do. What's due on Friday? The folder from Monday. So the folder that I'm talking about next Friday, right? And you won't have the folder due this upcoming Monday. So the 15th, that folder is going to be moved to Friday, which would be the 19th. So I'm just going to push everything back, and it'll be all updated this afternoon. What kind of things will be on our conversion sheet this time? You mean the equation sheet, I think? Basically any type of equation. However, I think I mentioned this on Wednesday, and I'll make a decision about it today. Currently, I am toying with the idea of making this an open note test, just because people love to complain about ProctorU, and I get it. It doesn't work all the time. So if that's the case, I would not give you a sheet at all. I would say you make your sheet. That's the trade-off. I won't give you anything. So you have to have a periodic table. You have to have an equation sheet. And then you can use the resources. But be aware that the time won't be different. And I do hesitate to do open note tests just because I have a fear that when people hear open note, they don't study as much because they say, oh, my notes are going to be there. And then they see the test and it's like, oh, crap, I don't know how to do it. Let me look it up. It takes 25 minutes to do one question, and then you still have the other 16 questions to do. So, but I will let you all know that later today. All right. So any other questions? All right, so one sec. While I clear up this writing. Okay, so just got a message from our SI Sarah. So Monday will be practice for the test. Wednesday, there will be no SI session, so you can focus on the test. So that's our SI schedule moving forward. But let's actually get into material now. Right, so we talked about the ideal gas law. PV equals nRT, and this is a combination of the laws we talked about on Wednesday, Charles' law, Boyle's law, Avogadro's law. And we can combine that into one simple equation that is used in general chemistry and chemistry in general when talking about gases. Pressure of a gas times the volume of a gas equals how many moles of a gas you have, that's N, multiplied by the gas constant, which I mentioned this on Wednesday, but the gas constant has different values depending on what version of the constant you use, times temperature. Temperature is always going to be in Kelvin. So I believe I ended up talking about this, but we didn't get to an actual question. So let's just get to this and practice using the ideal gas law, which I'll write down again, PV equals nRT. So I'll give people a minute or two, and I'll put up my little timer here to see where we're at. But what is the pressure in a 10-liter cylinder filled with 0.448 moles of nitrogen at 315? And here is your gas constant. So just a little simple calculation to get us started here. Oh, you think we did this already? Okay. If you already have stuff written down, we probably did. But I'll just do it again because it is super simple. Pressure is 10. Or sorry, one of the Friday ones. I want to know what is pressure. Still waking up here. Pressure unknown. Volume is 10 liters. N, 0.448 moles. R, 8.314 liters. Yeah, now I'm doing it again. I'm remembering it. Liters times kilopascals divided by K times moles. Moles cancel out. Multiplied by K, 315. K cancels out. So right now when I do that, 10P, so 10.0 times pressure equals, let me do this really quick here, equals 8.314 times 0.448 times 315. That's 1,173. So I'm just multiplying the right-hand side of the equation again. 1173.272. Divide each side by 10. The pressure is 107 kilopascals. Significant figure should be 3 because I did, yeah, now that I'm seeing this, I'm remembering R, the gas constant, does not have sig fig, so it's like pi, it goes on forever. You always want it to be in Kelvin. Yes, the gas constant, when you look at the units of the gas constant, it's always in Kelvin for the temperature. So all your calculations with temperature when using the ideal gas law have to be in Kelvin as well. Kelvin and moles are going to be the two consistent. The thing that changes the most for the gas constant are your volume and your pressure measurements, or what units they're in rather. So you just have to be aware when doing the ideal gas law, when selecting your R, you use the same units. You can't be mixing a kilopascal with an atmosphere. So that's our first foray into the ideal gas law. So here is another question, a little more complex, that deals with the ideal gas law. So I have a weather balloon and I inflate it to a volume of 28.5. Pressure is 748 torr. This conversion is wrong. 1 atmosphere is 760. So if we're given atmosphere, we don't need to convert it to Kelvin. Well, you can't do that. I think you meant kilopascals. So if we're given atmospheres, we don't need to convert to like kilopascals. Each gas constant has a you just match it up, right? So here, well, we're kind of actually doing a volume conversion, but yeah, or sorry, a pressure conversion. So we're going to look at that here. So weather balloon, volume of 28.5, pressure of 748, and a temperature of 28 C, right? So I do that, and I let the balloon rise 25,000 feet in the air, where the pressure is now 380 torr and minus 15 C. Assuming this balloon is free to expand and contract, what is the volume of the balloon at this new altitude? So this one is a little bit of a thinker. Draw pictures, start labeling what values goes to what variables. And again, the ideal gas law is PV equals nRT. Generally with PV equals nRT, you'll always have one unknown. So try and solve for that unknown and then see how far you can get with this problem. It's tricky. You have to do a couple calculations for this, but I'm going to let you to see if you can figure that out. Let me know if you have questions. I'll put up the handy dandy question timer. And yeah, let me know how you're doing. If you get stuck somewhere, feel free to send me a message and I'll try to walk through it. Otherwise, I will be back in a few minutes just to go over this. So to convert from Celsius to Kelvin, it is Kelvin equals Celsius plus 273.15. So a question that I thought would be relevant to a lot of people. Are we ignoring the first part of the data and focusing on the second half, what it's asking for? Well, let me just talk about that for a second. So if we just ignore the first half, right, and just say, okay, I need a volume at this second altitude. So if I just say, okay, this I'm just going to ignore, and I do PV equals nRT for the second part. So my pressure is this. My temperature is this. It's telling me that I need to find the volume. However, there's another piece of information missing here. How many moles do I have of my gas? That is not in the second part of this question at all. So if I do PV equals nRT, I have one equation and two unknowns, which means this equation would be impossible to solve. However, I like to draw pictures, right? So the balloon, the only difference between the balloon is that it just went into the air. The amount of gas in the balloon is never stated to change. So at ground level, we know, I'm going to write down PV equals nRT again. So in the first part of the question, I give you the volume at ground level. I give you the pressure. I give you the temperature. And we always know R because it's a constant. So in the first set of situations or variables, you can find out how much gas I put in the balloon. That would solve this problem. Now you know it. The balloon rises, and now you only have one unknown. You just have volume as your unknown. So that's how we use the two pieces of information in this problem. That's what makes this problem tricky. So if you're a little lost, that explains how to go about this. And I will start putting the math here in just a few seconds, as I just need to calculate it out myself. You're still lost? Okay, I will go over it in a second. No worries. All right, so let me work through this math then. And let me just go over that explanation again, as we still have people who are lost. Yeah, getting lost, I explained about what information is necessary. Yep. So to deal with that, because like when you're given a lot of information and just to know, okay, what information do I need to use to solve this? That's actually a very good example of, quote unquote, the real world, where you're just given a boatload of information, and part of your job as a human is to figure out what information is good. That's why we're better than computers. Computers, somebody has to tell them what information is good, what information is bad. Humans, we get to make that decision. So again, I have my picture here. So under my first conditions, I have a weather balloon, and it's inflated to a volume of 28.5 liters. So my volume, 28.5. My pressure is 748 torr. My temperature is 28 C. When doing problems with gases, always keep in mind the ideal gas law. You should be able, from the information I give you, try and match up the numbers to each variable. There's 4 variables, P, V, N, and T, because R is always a given. And what you should find out is that there should always be one variable you don't know. So under my first conditions, I know PVT, I don't know N. Let's look at my second conditions. I'm now 25,000 feet in the air, right? And under these conditions, I'm saying my pressure is now 385 torr. My temperature is minus 15 C. Assuming it can expand freely, calculate the volume. So it's telling me to calculate the volume, so I don't know it. And I was never given how many moles of gas are in this balloon. All right. So those are the 2 different situations, the 2 different conditions. And these are my ideal gas law variables. And the critical thinking part of this is to realize that even though I'm at 2 different altitudes, the gas inside the balloon itself never changes, in that you never lose gas, you never add gas. So you can figure out how many moles of gas you have at the ground condition and use that for the higher condition. Or another way to put that is that when you're using PV equals nRT, you usually have one unknown and you want to solve for that unknown. So let's do that in our ground conditions. Let's solve for N. Before we do that, we look at our R constant. Our R is in liters, atmospheres, mole, K. So all of our units have to match that. Our volume's in liters, so we're good there. Our pressure's in millimeters mercury, or torr, so we need to get into atmospheres. So we need to do a unit conversion here. So 748 millimeters of mercury for every 760 millimeters of mercury. These units cancel out. There's 1 atmosphere. So our pressure, instead of saying 748 torr, is 0.984 atmospheres, doing that conversion. Temperatures in C needs to be in K. So 273 plus 28 is 301.15. And only 4 digits are significant because we're doing adding and subtraction. All right, now we have all our units in the, all of our numbers in the right units. So we have 0.984, that's our P, multiplied by a volume, 28.5, equals N, don't know, times R, 0.08206, times T. PV equals nRT. 301.15. Solve for N by dividing each side by RT. And the number of moles of gas you have, if I did my calculation right, is 1.135059. Check our sig figs. 4 sig figs. R, we're just going to ignore that because R goes on forever. V is 3. P is 3. So our numbers should be 3 sig figs. 1.14 because that's a 5, and so we round up. So there's 1.14 moles of gas in my balloon. And going back to what I said previously, that's 1.14. The amount of moles in this balloon doesn't change, just the height does and the volume. So that's also 1.14 moles. Now we have PV equals nRT with only one unknown, our volume. So before I go into that one, let me just take a break here and ask, did Did I lose anyone there, or still confused about what I did with our balloons in this first condition here? Yay, glad to hear it. All right, so condition 2. Pressure, 385 torr. We don't want that. We want it in atmospheres. Same conversion. 385 divided by 760 is 0.506579. So 0.50, what did I say? 0.506579. Here, we only have 3 sig figs, but I'm not going to round until the very last part, because if you round too early, you can get rounding errors. Temperature minus 15.0, which is, let me do that. I can't do math in my head this morning for some reason. 258.15 Kelvin. Again, this only has 4 sig figs. Volume, don't know, and we just figured out. So let's plug this in. So 0.506579. These 3 are significant. That is my pressure. Volume, don't know, trying to solve that. And 1.14 R 0.08206. T 258.15. These are significant. So my final answer will only have 3 sig figs. And doing this calculation, solving for V, again, if I did all my math right, let me just double check that. 1 by 88, that times that times that, that looks good to me, is 47.465 liters. We said 3 sig figs. That's a 6, so that rounds up. 47.5 liters. That is the volume of our balloon at a different height using the ideal gas law in a balloon that's free to expand. And like I said, this question is quite more complicated than what it seems, where the big piece of information that is not actually stated in the problem is you have to realize the moles of gas you have to figure out in the first condition and use that for the second condition. So definitely one of those critical thinking questions that people love to talk about. But now that you've seen that all laid out, questions about this type of logic, this problem, or using the ideal gas law? So dumb question, but in one condition, if we only have one variable to find out, should we figure that one out first? Yes, in general, with the ideal gas law, the way that problems work in the ideal gas law is that there's 4 variables that are potential unknowns, right? PV and NT. R is always a constant. And the way that these problems are always set up is that if you're given multiple conditions, one condition will always have one unknown, or some way to reduce it to only one unknown. So that's what you want to tackle first. And then, yeah, if you get like that unknown, you could apply it to other conditions based on what the question says. You really have to pay attention to see if your pressure and volumes and temperatures are changing. But yeah, in general, that's how it goes. So you didn't convert the millimeters of mercury to atmosphere and got the right answer, and you're only off by 0.1. That is interesting. It could be that it just happened to work out this time. I don't have a good explanation why that would be, because they should be still off, because the gas constant does depend on the unit. So I think it might have worked this time because we have two different conditions and possibly the units have canceled out. That's a complete wild guess that I don't even believe after I said it out loud. I'm going to put that up to a weird quirk of math and say to caution you that that is usually not the case. But who knows? Just make sure you check your units because it does matter quite a bit. All right, moving on. So we talked about the ideal gas law, and now let's see some of the things we can understand or calculate using the ideal gas law, and that gives us the molar volume, density, and the molar mass of a gas. So some definitions for us. Molar volume is volume occupied by a mole of gas. So what is the mole of gas? Or sorry, what is the volume of 1 mole of gas? And when we do certain calculations, not all calculations, but certain calculations, there's something called standard temperature and pressure, STP. Those of you who enjoy racing might have heard STP before. What STP is just a set of variables that chemists agree on when measuring certain properties about a gas, because gases change based on their temperature and pressure. So if we want to look at other properties of a gas, we just say keep temperature and pressure the same. We're going to use our standard. Standard temperature and pressure is 273 Kelvin in 1 atmosphere. Therefore, if you're looking at the volume of 1 mole of gas at STP, we can use PV equals nRT and rearrange it to solve for P. So this is really just PV equals nRT, right? Take each side, divide by P to get V equals nRT divided by P, right? And if I'm looking for the molar volume at STP, well, molar volume is occupied by 1 moles of gas, so N is 1. R, constant. Temperature, standard STP, is 273. Pressure, 1 atmosphere. So the volume, and this is also molar volume, of a gas at STP is always 22.4 liters. And under the ideal gas law, it does not matter what that gas is. That's one of the drawbacks and one of the good things about the ideal gas law. So it's like a double-edged sword there. When we use the ideal gas law, we don't care about the gas. Every gas follows the ideal gas law. So that's good because it simplifies our life. It's also bad because that's not reality. Gases do change a little bit based on what they are, but under STP conditions, it's a good enough approximation. One thing I want to caution you about this slide that happens every year. It's very possible on the test, I ask you a question about calculating molar volume. And it's very possible on the test that I ask you to calculate molar volume at conditions different than STP. Yet when I do that, I expect that a lot of people will put down 22.4 liters because they memorize it. Keep in mind, 22.4 is the molar volume only at STP. Under different temperatures and pressures, you have to calculate volume using PV equals nRT. So don't memorize 22.4 liters. That's a worthless thing to remember. just remember what molar volume is, what the definition of molar volume is, and remember what STP means. STP means 273 Kelvin in 1 atmosphere. Right, so let's take a look at some problems dealing with this type of information. So I want you to tell me, what is the volume of 33.6 grams of neon at STP, given the gas constant here? So I'm going to give people a few minutes to try and come up with an answer for this. As always, if you have questions, let me know. And whoops, did not mean to hit that button. I meant to put up the poll to see where we're at. Whoops. Sorry, getting click happy here. There we go. So yeah, if you have questions, let me know. Otherwise, I will let you try and solve this. All right, so we do have some people finishing up, and for the sake of time, I will just go ahead and start working on this. So, as always, when dealing with ideal gas law, PV equals nRT, write down my equation, start putting my variables. So we're at STP, so that gives us two variables. That gives us pressure, 1 atmosphere, gives us temperature, 273 Kelvin, right? And so we have 2, determine the volume. So the volume is what it's asking for us. And N is moles of gas. Well, we don't have moles right now. We have 33.6 grams, but we already learned how to convert grams to moles. That's using the molecular mass. So neon, if we look in our periodic table, neon, element 10, is a molecular mass of 20.180 grams for 1 moles. Grams of neon per mole of neon. Grams cancel out. I'm left with moles of neon once I do 33.6 divided by 20.180. That is 1.6650 moles of neon. Since 33.6 has 3 sig figs, I'm going to make a little note to myself and say there's only 3 sig figs here. But again, I'm going to keep all the digits so my calculation is more accurate. So I don't get what's called a rounding error. All right, so we have 4 variables, 1 unknown. So I'm going to already put it in the version of PV equals nRT we saw in the previous slide of V equals nRT divided by P, which is 1.6650 and R 0.08206 T 273 divided by 1. So my volume then is 37.3003 liters. Check my sig figs, and it should be 3, temperature is 3, and our N was 3. So it's going to be those 3. 37.3 liters is my volume at these conditions. All right, questions about what we did here? Pretty straightforward with the ideal gas law. Let me just see. Okay, so we have a couple more. At what conditions will you get 22.4? You'll get 22.4 if there's only 1 mole of gas at STP. Here we had 1.66 moles. That's why we got a bigger volume. Yep, that's kind of why I mentioned like don't memorize 22.4. It's only for 1 set of conditions. It's more important to know how to do the calculation so you can do any conditions. All right. So we'll do one more topic and then that will be it for like test 2. And the topic that we're going to look over is, sorry for that. It's density of a gas. And density of a gas is simply the molar mass of a gas divided by molar volume. So again, just as a reminder, even though we covered this like only 10 minutes ago, molar volume is the volume of 1 mole of gas. If we're at STP, molar volume is always 22.4. But like I said, we could actually calculate that. So I do recommend not to memorize 22.4. You can just always recalculate that. But define the density of the gas, just molar mass divided by molar volume. So here's the density of helium versus the density of nitrogen. So that's why helium balloons will float, is because the atmosphere is roughly 70% nitrogen gas. Most of the stuff we breathe is nitrogen, which has a weight of 1.25 grams per liter. Helium has a much lower density, 10 times lower. So helium will float on the nitrogen atmosphere. So generally, anything that is lighter or less dense than nitrogen floats. anything more dense or the same density as nitrogen doesn't. That's why if you breathe into a balloon, it doesn't float because it has the same density as the air around it, because you breathe it in and you don't change it and then you breathe it out. While if you had a helium balloon that you fill up at the store, that does float. All has to do with density of gases. So the last question that we're going to look at is, what is the density of hydrogen gas at 20 C and a pressure of 1,655 psi? I give you the conversion from atmospheres to psi right there. And pesky sneezes. And the density, remember, is molar mass divided by molar volume. So tell me, under these conditions, what is the density of our gas? So I'll give people a couple minutes to do that, and then I'll come back with the answer just before we wrap up. And hydrogen gas, by the way, is H2. Right. Time is running short, so it's okay if you haven't quite finished. Hopefully you got to the point at least like looking at variables and at least trying to formulate a plan of action. So I'm going to go through and PV equals nRT again. So there's two things that we need to figure out for density. We need the molar mass and we need the molar volume. Molar mass is from the periodic table, right? So the molar mass of H2 is the weight of hydrogen times 2, which is 1.008 times 2 is 2.016 grams per mole. So that's the molar mass of H2. That's easy to figure out. Now we need the molar volume. What is the volume of 1 mole of gas under these conditions? So let's figure out our variables. Pressure is 1655 psi. Our gas constants in atmospheres, though, so we don't want to be in psi, we want to be atmospheres. So we can convert that. For every 14.7 psi, there's 1 atmosphere. PSI cancels out. And this means when we do this calculation, we are looking at, and this should be 4 sig figs. Actually, yeah, it should be 4 because that's an exact number. So the reason why I said 4 and not 3, I'm sure people are wondering that, is because this 14.7, this conversion factor goes on for a lot longer than just the 7. So usually when I do conversions, you kind of ignore that and sig figs, and you just look at the original number, 1655. So 1655 has 4 sig figs, so our conversion should have the same sig figs as our original number. So in case you're wondering that. So 4 sig figs. Atmospheres. So 112 atmospheres. So imagine 112 times the weight right now on you. You would be crushed into a little cube. But that is the pressure on this gas right now. Our PV, we don't know because we're trying to solve that. N, this is molar volume. So N is always 1. And that goes on for infinite amount of sig figs. So 1 mole. T, we're at 20 C plus 273.15 equals 293.15. Using our addition and subtraction rules, that will have 4 sig figs as well. Now we can solve for V. So I'm going to rearrange PV equals nRT to do V equals nRT divided by P, which is N is 1, gas constant, 0.8206. Temperature is 293.15, 4 sig figs, divided by pressure, 112.585, 4 sig figs. Solve for my volume now, 0.213669 liters, because my gas constant's in liters, so that's what my volume is. Look at my sig figs, see that I have to keep 4. It's going to be those 4, because remember the 0 in front is not significant. So I'll go 6, 6. This 6 is greater than 5. Round up to 7. And that is the volume of 1 mole of gas under these pressure and temperature conditions. So to find density, I do molar mass, 2.016, divided by molar volume, 0.2137. And that gives me 9.435 grams per liters. And it's grams per liters because this unit's actually liters per mole. And so when you do molar mass, which is grams per mole, divided by molar volume, which is liters per mole, the moles cancel out and you're left with a unit of grams per liters. All right, so that's the last question we're going to do here. Any questions about that, like that logic, that thought process, or anything else that we have covered today to deal with gases, or anything about the tests you would like to ask while you still have me here right now? N equals 1. Because we are finding molar volume. That's correct. So molar volume is the volume of gas when you have 1 mole of it. So anytime you see the word molar volume, that is telling you N equals 1. Just like how STP, if you see STP, that tells you temperature is 273 and pressure is 1 atmosphere. Will we have the solubility rules on the test? Yes, if you... So either way, yes. If I decide after making the test that I still want to use Proctor U, on the equation sheet, you'll have the solubility rules. If I have open note tests, you'll have open note, so you'll have it anyways. So either way, yes. Again, I'll make that decision today. I'm going to try and finalize the test today and let you know about which way we're going to do the test. Any other questions people might have? So what we covered today is the last bit on the test. Yes. Anything we cover on Monday will not be on the test. Correct. So basically the ideal gas law up to ideal gas law and density of gases is going to be it. I think, let me just see. Yeah, question 5 is another question that has to do with density. So it's good practice to try and do that. All right, so I don't have anything left to share with you. Seems we do. Yep, no problem. If you have questions while studying or anything like that, please don't hesitate to reach out. I'll be happy to answer you this weekend. If you want to set up a meeting and go through more example problems, I'm always happy to do that as well. Otherwise, I'm going to get some more coffee because apparently I didn't sleep right and I'm still tired. And I will see people on Monday. Take care, everybody.